So we'll start with part one, always a good place to start. So we're going to take a known amount of the oxalate, C2O42-, that there, and we're going to react that up with a permanganate solution. And if we know the amount of oxalate and we measure how much permanganate solution we need to react with all that oxalate, then we can determine the concentration of the permanganate solution. Before I go on, I want to detour ever so slightly and expand upon this equation, what it means, and what it actually relates to real live compounds. This is a net ionic equation. What I'm interested in is the reaction of this anion oxalate with this anion permanganate. Okay. However, I can't just go to a shelf and find a bottle that says oxalate on it that contains C2O42-, because any anion has to have an accompanying cation. And so in this experiment, I'm going to take ammonium oxalate. The ammonium is there because it's part of the compound, but when I put it into aqueous solution, the ammonium oxalate ions dissociate, they split up, and the ammonium is floating around as a spectator ion. It's not involved in this particular reaction. Same idea with the permanganate. The MnO4- is the really important species that's involved in this reaction. But again, I can't just go to the shelf and find a bottle that says MnO4- and pull out a whole bunch of permanganate. There's got to be a cation that goes with that. And the cation that we have in this case is potassium. So the bottle is labeled potassium permanganate. I dissolve that up in aqueous solution. It dissociates because it's an ionic compound, and the potassium ions are just floating around as spectator ions. Okay, so when we're studying the reaction, really all we're interested in are the oxalate and the permanganate. But you always have to have at the back of your mind that the oxalate was accompanied by ammonium. The ammonium's floating around as spectator ion, but was important at the start. And the same thing for the permanganate. There's potassium ions floating around. They're just boring, uninteresting spectators. So with that in mind, how do I get a known amount of oxalate? Well, I go to my shelf and I pull down the bottle that's called ammonium oxalate, and I weigh out a certain amount of that. Now, if I record that exact mass, that means I know the mass of the ammonium oxalate, which means I've got a known amount of the oxalate. I'm then going to add 50 cubic centimeters of water, so that will dissolve it up to make the ammonium oxalate solution, which means that's got the oxalate floating around in aqueous solution. Add in some 3 molar sulfuric acid. We need the acid in there to give us the acidic conditions for the reaction, and swirl until all the solid, the ammonium oxalate, has dissolved. Then I fill a burette with the potassium permanganate solution. Again, this solution has potassium ions that are boring and permanganate ions that are interesting. We're going to add about 10 cubic centimeters of this to the oxalate solution and swirl. So I'm going to start the reaction off by just measuring in a known amount of the permanganate solution. Doesn't matter exactly how much of it I add in, because all I'm doing here is I'm starting the reaction. I then heat the solution gently to about 80 degrees Celsius, and I put this in red to emphasize it to you because there's a post-lab question about this, till the color has disappeared. Now, why would the color disappear? Well, I took a colorless solution of oxalate and added in some purple permanganate solution. And that permanganate is going to react with the oxalate, and every bit of the permanganate that reacts makes a colorless Mn2+ in the solution. So by heating until the color has disappeared, what I'm saying there is that I have no more of the permanganate that I added in left. In other words, all 10 cubic centimeters of this has reacted up. Now at this point, I'll take away the heat and I'll continue to titrate. In other words, I'm going to add a little bit of the permanganate and see what happens, and a little bit of the permanganate and see what happens, and a little bit of the permanganate and see what happens. And of course, every little bit of permanganate that I add that reacts goes from purple to colorless. And then it says I should continue until a pale pink color persists for at least 30 seconds. Now, I debated making this a post-lab question, but that would, I think, mess things up as we're going through. So I'm going to tell you what this pale pink color means. We've got the oxalate, we add purple, the purple reacts and becomes colorless. We add a bit more purple, it reacts and becomes colorless. We add a bit more purple, it reacts and becomes colorless. Are you bored of this yet? We add a little bit more purple, and that's just enough to use up all the oxalate. So that purple goes colorless, but now there's no more oxalate left in there. So the next teeny little bit of purple that I add in doesn't react. Now, of course, purple, when it's really diluted, is pink. So this pale pink color is the indication that we have finished the reaction. This pale pink color, it's called the end point because we're seeing something with the titration, and we hope that it reflects the equivalence point at which I've added just the right amount of permanganate to be equivalent to all of the oxalate with which I started. Then at that point, you record the total volume of the potassium permanganate solution added. In other words, that's the about 10 cubic centimeters that you added at the start, plus the bit that you have added with the titration. Now, don't worry about understanding every little step that we did here, because of course, as you know, anytime you do an experiment, a lot of times you don't quite get the hang of what's going on until you actually do it. So now what I'm going to do is I'm going to do each of these steps showing you how I did it in the lab.